Okay, so let's consider a system. So here is a rod attached to some cart, and this cart can move on this horizontal, on a horizontal surface. So there's some horizontal surface here, and there's no friction, but we attach not just a simple pendulum here like that, and let's make the length of the pendulum B, but we attach another one. The mass of the pendulum ball is M. We attach another one to this one, also of the same length. That's the string, and another object, another pendulum ball of mass M. And so the system can move on this horizontal surface. What are the equations of motion? What are the quantities that are conserved? So we need to find a coordinate system, right? The last thing we want to do is figure out how to do this using F equals ma with tension forces here, gravity pulling these things down. But it's not too complicated to find a coordinate system. We want, let's think of a coordinate system that looks like this, like some X and Y coordinate system. So we have an angle, so the X value this angle can change, so let's call that theta 1. The angle here, with respect to the vertical, let's call that theta 2. Let's make the mass of the cart twice m. And so let's find the position. Let's find the derivative of the positions of the three objects, and then we can construct the Lagrangian. So the position, let's call this object 1, 2, and 3. So the position, two-dimensional space, x and y, for object 1 is x plus, the part along here, which is b sine theta. So we have b sine theta 1, that is the x component, plus something j hat, and then the y component is right here, so that's minus b cosine theta 1, that's j hat. Okay, that's the coordinate for that object. This object has a position, R2, which is, it's attached to that one. So we have an x plus, the x value of the object labeled 1, plus the same thing here, we have to add its x part here. And so that is plus b sine of the other angle, sine of theta 2. And that's the x component. And the y component is, they're both negative, right? Because we have this, so we're adding to this, we're adding that, but they're both below the origin. So we have minus b cosine theta 1 minus b cosine theta 2. Maybe we can write this as minus this plus that, so that we can put in a j hat like that. And the position of this one, R3, that vector is simply the x value plus, some y value, some y star. Well, that's a negative value. So it's a minus y star, however far below that is. Minus y star j hat, but that's a constant, obviously. So it won't affect anything. So let's find the derivative. So we have our dot, or rather R1 dot, that is x dot plus derivative of this term gives us a theta 1 dot b cosine of theta 1. And then we have a plus theta 1 dot. We're taking the derivative of this, so we have theta 1 dot. We have the b, and we have the sine of theta 1, and that's the y component. Okay, right, we're going to construct our kinetic energies from these, and then we have R2 dot, which is x dot plus theta 1 dot, same as what we had before, b cosine theta 1, plus the same for the second term. We have a theta 2 dot, b cosine of theta 2, that's the x component, and then we have plus theta 1 dot b sine theta 1 plus theta 2 dot b sine theta 2 j hat. And the derivative of the R3 in time, R3 vector, is simply x dot I hat. Okay, so we can construct the kinetic energy. The kinetic energy is K equals to, well, let's do them one by one. So we'll have m over 2 times R1 dot squared. All right, so that gives us x1 dot squared plus theta 1 dot squared, b squared, cosine squared of theta 1, plus twice x dot theta 1 dot b cosine of theta 1 plus theta 1 dot squared b squared sine squared of theta 1. And now we'll do the same for the second object, this one. So that one, similarly, we'll have m over 2, x dot plus theta 1. Well, let's, we have to square these. Theta 1 dot b cosine theta 1 plus theta 2 dot b cosine theta 2. We have to square that, plus theta 1 dot b sine theta 1 plus theta 2 dot b sine theta 2. We have to square that. The x dot squared and the y dot squared, plus the last one is simple. We have 2m over 2 times x dot squared, and the potential energy is our reference point is here, and the objects are below that. So we have a minus, minus y values, minus mg b cosine theta 1 minus mg b cosine theta 1 plus cosine theta 2. There's no potential energy for this object because it's well, actually, that's not true, but it's there's a constant there, and that's not changing, so it's not going to affect anything. So really, we should have a whatever that coordinate is. What did we have? A y I think it was y star. So we have a minus 2m g y star quantity. It's a constant, so we don't worry about it. So the Lagrangian, let's write the Lagrangian. Then we can find the equations of motion. So the Lagrangian is let's see, m over 2. Well, it's kind of silly to write everything over again. It's just k or t, whatever we want to call kinetic, k minus u. So it's just this term, and then we bring in this with a positive. Okay, so in the next video, we will work on the Euler equations and find the equations of motion and the constants.